Welcome to the last plenary talk of the conference. It's a great pleasure to introduce Professor Arno Rauschenbeutel from Humboldt University zu Berlin and Universität Innsbruck in Vienna. Arno came last year to give a great talk in the American Physical Society special session, and we are all excited that he accepted this invitation to give a plenary talk this year in the context of single atom imaging using metamaterials related concepts. Thanks very much.
Okay, thank you very much for the introduction, and thank you to the organizers for inviting me. It's a great pleasure to be here and to present our work. As advertised, the title is Seeing a Single Atom Where It Is Not, and I will try to explain over the next hour or so what we mean by that. So the work that I will be presenting was carried out in my group at the Vienna University of Technology, and it was also a collaboration with the group of Rainer Blatt at the University of Innsbruck, and the main people involved on my side were the PhD student Stefan Walser and the senior scientist Jürgen Volz. And in Rainer's group there was Gabriel Araneda, Daniel Higginbottom, who is also a PhD student at ANU Canberra, and the postdoc Yves Colombe. So, as already announced, also, I recently changed my affiliation, and I would like to take advantage of this talk to place a shameless ad. So we recently, I'm since the 1st of January professor at Humboldt University in Berlin, and my group will move there next year. And with this move, there's a number of PhD, postdoc and senior scientist positions opening. So in particular, if you are actually interested in a permanent position and are skillful in nanofabrication and nano-optics, then talk to me, please. So it somehow feels like carrying coals to Newcastle in front of this audience to give this introduction, but let me just remind you that we are used to the fact that when the optical elements that we use to guide and control the light field and the interaction of light and matter get smaller, we need a more precise description of the light, so we can actually understand bulk optics basically in terms of geometrical optics and rays. And if we want to understand diffraction and interference, we have to go to the wave description, but it's mostly still scalar theory that will do the job. But if we go to optical phenomena at a size smaller than the wavelength of the light that is involved, then we actually have to go to a full vectorial description, and the propagation of light and the polarization properties can no longer be considered independently of each other. And to give an example, in the first part of my talk, I will actually be reporting on some experiment that we did about 4 years ago, where we coupled gold nanoparticle and the plasmonic mode of such a gold nanoparticle to the light guided in an optical nanofiber, which is a dielectric waveguide with a diameter smaller than the wavelength of the guided light. And you will see that due to these complex polarization structures and the behavior of these polarizations as a function of the propagation of light in the waveguides, surprising phenomena can be encountered. So that will be a kind of introductory part of my talk, but then the essence of what I will be showing you then is that the same phenomena also happen when you go to bulk optics. And there are actually situations where you can not consider the mode and its polarization as being independent, and there are like fundamental implications on the interaction of emitters with modes that are collected or guided with just lenses. Okay. So if we consider now as an example for a nanophotonic structure the guided mode in such an optical nanofiber, so we are dealing with a silica waveguide with a diameter of about 300 nanometers, and we're dealing with light at green light at a wavelength of 532 nanometers, then the polarization properties of these modes are of course described by Maxwell's equations, and actually if you want to understand the polarization in, for example, the evanescent part of the guided mode. So here I plot the electric field as a function, or the electric field amplitude as a function of position, and here's the center of the fiber, and you see the strong gradient of field outside of the fiber. Then the part of Maxwell's equations that tell us about the polarizations is just Gauss' law. So the electric field, or the divergence of the electric field in the evanescent part of the guided mode has to fulfill the condition that the divergence vanishes. Okay? And if we now consider a guided mode, which is translation invariant along z, okay, then we can just write it as an amplitude which depends on the transverse coordinates and a phase vector e to the ikz for the propagation along z. And if I now apply Gauss' law to such a field, then I immediately see that when I send a paraxial light field, which is linearly polarized, into such a waveguide, we actually get longitudinal components, so a component of the field that oscillates along z. So in addition, in the waveguide, when I send such a light field in and I look on top or below the fiber, in addition to this linear transverse component, I do get a longitudinal component, and this longitudinal component is proportional to the field gradient here along y, so this is the vertical direction y, and of course the field gradient along y changes sign above and below the fiber. So that means that the sign of this longitudinal component is opposite above and below the fiber. And in addition, there is a very important part of this equation, which is this phase vector I here, which means that the transverse and longitudinal components oscillate pi half out of phase with respect to each other. That means that the interference of these two field components gives rise to elliptical polarization, and actually the magnitude here of this longitudinal field component is proportional to the field gradient of the transverse component multiplied by a small length scale, which is the wavelength over 2 pi. But if the field gradient is significant on this length scale, which is the case for an evanescent field, then the longitudinal component can be as large as the transverse component, so that the polarization is, to a good approximation, circular above and below the waveguide. However, this circular polarization is very different from the circular polarization that you know from paraxial light fields, because while for a paraxial light field like a laser beam, which is circularly polarized, the electric field turns in a plane which is normal to the direction of propagation, here the electric field spins in a plane that contains the direction of propagation. So it behaves like the blades of the rotor of a helicopter. The light goes in this direction and the E field turns like this. Now, I can quantify this elliptical polarization in terms of an ellipticity vector, which is a vector that is normal on the plane in which the electric field spins, and its unity if the field is circularly polarized and gets smaller when it's elliptically polarized. And it turns out that this ellipticity vector is the same quantity as the spin of the light field, where here spin is a classical quantity, it refers to the intrinsic angular momentum carried by the light field. So if you put an absorbing particle here, it will start spinning about an axis that points out of the board. Okay, it's normal, so we're talking about transverse spin of light in this context. And what you see is that this transverse spin of light changes sign when you go from above the waveguide to below the waveguide. For symmetry reasons, that is kind of obvious, that when it turns clockwise above the waveguide, it has to turn counterclockwise below the waveguide. So the local spin depends on the transverse position in the mode, and this effect is referred to as spin-orbit coupling of light. Okay. For the following, what is also important is the fact that if I now change the direction of propagation of the beam, so I send my light not from the right but from the left into my waveguide, then this is the same as running this movie here backwards, and then of course if the field turns clockwise for left propagating light, then it has to turn counterclockwise for right propagating light. So this means that the local spin, this transverse spin of light, changes sign with the direction of propagations. So the spin of the light field and its linear momentum are no longer independent quantities, but they are one-to-one locked. One also speaks about spin momentum locking of light in this context. So that means that when the light propagates in this direction and the transverse spin above the waveguide points in this direction, when I reverse the situation, then when the k vector changes sign, so does the spin. Okay. And now, knowing this, we find that this has important implications for spontaneous emission of emitters into this waveguide mode. Okay, because if we now place an emitter on the nanofiber surface, say a gold nanoparticle, and we optically excite it by sending, for example, green light onto it, such that its dipole turns clockwise, then the only optical mode in the nanofiber that can accept this polarization is leftward propagating light. So the nanoparticle will emit its light into the waveguide, but it's a directional spontaneous emission. Okay? And if I now change the sense of rotation of the dipole and make it rotate counterclockwise, the light will be emitted to the right. So this means that the polarization of the emitter now defines the direction of emission. And one also speaks about chiral coupling in this context. And actually chiral in this context means probably something different from your favorite usage of the word chiral. So here it's synonymous for propagation direction dependent. So every time you read chiral, you should replace by propagation direction dependent. Okay. And so we did such an experiment in 2014. It was published, but I would also like to stress that this phenomenon of directional or chiral coupling is not limited to our experimental platform. It has been observed in various settings. It invariably occurs when you have a strong transverse confinement of the light field, because remember, this longitudinal component is proportional to the transverse intensity amplitude gradient. Okay, so to my knowledge, it has been first observed with surface plasmon polaritons, excitations of metal film on a surface by illuminating a slit, and then seeing that when you illuminate that slit, the light goes preferably here to the left. with dielectrics, it has been observed with 1D waveguides, and here quantum dot coupled to 1D waveguides. In our group, we first came across the phenomena when studying cavity quantum electrodynamics, where we couple a single rubidium atom to the whispering gallery mode in a whispering gallery mode, or to the evanescent field of the whispering gallery mode in a whispering gallery mode resonator. The same thing happens when you just put a gold nanoparticle on a dielectric interface or a 2D waveguide, and it can also be realized in photonic crystal waveguides. And when you look at the years of publications, you see that all these things happened more or less independently and at the same time at different places. Okay. So if you want to learn more about this chiral coupling and how in particular it affects the interaction of light and quantum emitters, then you could have a look at a review article that we wrote together with the groups of Peter Lodal and Peter Zoller in Nature. And however, I would now like to move on to the next part, or the main part of my talk, which is actually related to the fact that the same physics that I was now presenting for structures that guide the light turn out to also happen in free space. Okay? Because if you look at, say, a focused Gaussian beam, fundamental Gaussian beam, and you consider a beam which is linearly polarized in the plane of the screen, then we also have a strong field gradient here. If it's strongly focused, it's stronger, of course, which changes sign on both sides of the beam axis, and the light field has to fulfill, as before, Gauss' law. And that means that if I have a significant field gradient here, then I also get a significant longitudinal component which changes sign on both sides of the beam axis. And again, there is a 90-degree phase shift, meaning that I get elliptical polarization above and below the beam axis, and a transverse spin of light that points out of the board above the beam axis and into the board below the beam axis. So again, we see that there is spin-orbit coupling. So the spin, the transverse spin, depends on the transverse position in my mode. And also, if I now reverse the direction of propagation, the transverse spin will flip its sign and point into the board above the beam axis when the light goes from right to left. And now the question is, how does that affect the interaction of such a light field with an emitter? And the answer is yes. And to just get a glance of the underlying effects, let me just consider the situation where we are collecting the fluorescence of a circularly polarized emitter, where the electric field now spins in the plane of the screen, okay? If I want to collect this, then what I could do is just place a lens and a photodiode, okay? But then the lens plus this photodiode defines an optical mode, okay? So I place my emitter now in the optical mode, and now the question is, when do I get the most light integrated over the whole area here onto this photodiode, okay? And okay, if the emitter is on the optical axis, then equal amounts of light, of course, for symmetry reasons, will be emitted towards the photodiode and away from it. And if I just consider the scalar character of the light field, then I know that this Gaussian mode that I defined here will decay in intensity, or in other words, the coupling strength would just decrease when I move my emitter away from the optical axis. However, above the optical axis, the polarization of this mode is better matched to the polarization of the emitter. That means that if I now move the optical system such that the emitter sits above the optical axis, actually I get more photons hitting my photodiode, because while the intensity only decreases to second order because I'm at the maximum of my mode, my polarization gets more elliptical and I get a better overlap of the dipole. And I also get an imbalance of emission to the right and to the left with respect to this shifted mode. Now, if I was to use this system in order to determine the position of the emitter, then the natural thing to do would be to scan now my system and find out when do I get the most photons onto my detector. And then I say, okay, so now my emitter is on the optical axis, if I just take the scalar theory. However, the most photons arrive on the detector when my emitter is shifted. Now, if this is true, integrated over the whole detector, then I could also say, now what if this is a CCD camera, and I divide my photodiode into many photodiodes? Then, of course, all the photodiodes will exhibit this same effect. That means that I also expect such chiral effects of chiral coupling in free space to affect the imaging of the emitter. So with this, I come to the overview of the remainder of the talk. I will first now discuss these chiral effects in imaging of a point-like dipole emitter, and then I will present two experiments, one on imaging a nanoplasmonic emitter and one on imaging a single atom in a Powell trap using just regular microscope objectives. Okay. So actually the easiest way to understand the chiral effects in imaging is to consider the phase front of the light that is emitted by such a circularly polarized emitter where its field spins in the plane of the board, okay? So while this phase front, when you're far away from the emitter, looks more or less like a spherical wave, it turns out that since the emitter is just spinning, okay, the electric field is spinning, the phase front is actually not a spherical wave, but it is a spiral, okay? Because the perturbation propagates with the speed of light away from the emitter while the E field is turning. So that means that I get a spiraling phase front. Now that means that if I place the emitter on the optical axis of an imaging system here, and I place it into the focus of a lens, for example, which has focal length f, then the phase front does not cut the optical axis at a right angle, as would be the case for a spherical wave, but it cuts the optical axis at an angle which is slightly different from a right angle. Of course, the difference gets smaller and smaller the further I go away from the emitter. And now if this tilted spherical wavefront here hits my lens, it will be converted into a plane wavefront. However, this plane wavefront is tilted by the same angle alpha here. And this angle alpha can be easily computed or even read from this picture here, because what happens is that I make 1 lambda of progress when I go once around the emitter, okay? So that means the angle alpha is just lambda over the circumference here at the lens, which is 2 pi times the focal length. So then you see that if I make my focal length longer, my angle alpha gets smaller. And if I now send this light in the far field on a screen by either putting another imaging lens or just sending it at a large distance, I will get a point spread function of my emitter, and the centroid of my point spread function will be shifted away from the optical axis because of this tilted k vector of the wave here, okay? And now you can ask, so if I now try to find the position of my emitter, where is it? Well, what you have to do is you have to go backwards here and extrapolate to the object plane of the emitter. And that is easily done. You just have to multiply the angle alpha by this distance here, which is f. But then you see that that means that the focal length drops out, and the shift that you get here, apparently, of the position of the emitter by extrapolating the centroid of the point spread function back to the object plane is given by lambda over 2 pi. Okay? And that is independently of all parameters that I showed here. Lambda over 2 pi. That sounds like a fundamental result. And it turns out that this was already understood and predicted more than 80 years ago by Charles Darwin. So that's the grandson of the evolution theory Darwin, and the Darwin of the Darwin term in atomic physics for the experts. and he wrote an article on the theory of radiation, considering the emission of light by atoms. And there he considered now a circularly polarized emitter, and he found and describes that the wavefront of the emitted radiation faces not exactly away from the origin, but from a point about a wavelength away from it. It implies, and now this is almost poetic, okay, it implies that the photon, which is to carry away the energy and angular momentum from an atom of radius 10 to the minus 8 centimeters, starts its life outside the atom at a distance 10 to the minus 5 centimeters away. Okay? So that pretty much went unnoticed, because you should notice that still this is a very short length of 100 nanometers, okay? So this seemed like irrelevant. However, in the context of ultra-resolution microscopy, you are well able to resolve these effects, okay, nowadays. And this is why we went to try to see, actually, this shift of the emitter. And there's one other thing that, so I would like to stress in this context. So Darwin didn't say anything about the geometry of the whole experimental setup, right? It was a fundamental statement. And actually also here I didn't say anything about the parameters. The result is lambda over 2 pi. It turns out that this lambda over 2 pi shift is indeed largely independent of the numerical aperture of my imaging optics, and it's also largely independent of defocusing, so it's not a delicate effect, okay? And something that went unnoticed in the work by Darwin, because he was considering atoms which either emit a circularly polarized photon or linearly polarized photon along the quantization axis. But if you look for emitters that are able to emit elliptical polarizations, then we will see that even larger shifts than this lambda over 2 pi can be obtained. Okay. So in order to understand this, so the larger shifts as a function of polarization, we have to consider now no longer just a phase front, or it's not easily understood in terms of a phase front, but we should rather think about the circular polarization to be the interference of two linear components, okay? So we first have a component that oscillates in a direction orthogonal to the optical axis. And such a linear dipole then radiates a dipole emission pattern, but it's of course symmetric with respect to the optical axis. So if I image such a linearly polarized emitter, then I will just get a point spread function which is centered on the optical axis, okay? And now when we look at the circularly polarized emitter, then in addition I have this longitudinal component, and as we discussed, we will see a shifted point spread function, shifted by the equivalent of lambda over 2 pi. Now, to understand this in terms of interference, we have to now decompose the field into these two components. And the field that corresponds to the transverse dipole is then basically such a bell-shaped field, okay, which has its maximum on the optical axis. So this corresponds to the field oscillating along y. But if we now also have a dipole oscillating along x here with a phase shift of 90 degrees, then this dipole alone gives rise again to a linear dipole emission pattern. However, there's no emission along the optical axis. So if I now put a finite aperture, numerical aperture lens here, what I will then see is a donut-shaped mode, okay? But this donut-shaped mode comes from looking at a dipole that oscillates in your direction. So it turns out that the field changes sign, or the phase changes by pi, when I look from above the optical axis or below the optical axis onto the dipole. That means that if I plot the real part of the electric field of this dipole, it changes sign on both sides of the optical axis. And if I now interfere my symmetric bell-shaped dashed, so this dashed was the bell-shaped symmetric field component coming from the transverse dipole, and this dispersively shaped donut mode here, which has a field gradient, then what you see is that the sum of the two gives rise effectively to a shifted bell-shaped field distribution, okay? And now, looking at that, it also becomes clear that if I now enhance the amplitude of this field component, so I increase the field gradient of this donut mode here by increasing its amplitude, then I will get a larger shift. Okay, so and this shift is actually proportional to this field component here. So for, as we said, for the linear polarization, for circular polarization, the shift is lambda over 2 pi, but if I now double the amplitude of this longitudinal dipole, then the shift will be just 2 times lambda over 2 pi. And as a general result, that means that the shift that I observe will be proportional to lambda over 2 pi, and the proportionality factor is the ratio of the linear dipole along the optical axis divided by the transverse dipole amplitude, transverse to the optical axis. Okay? So this here is then the ratio of the major and minor axis of the polarization ellipse here. But then if you look at that result, you should say, hold on, this here can be arbitrarily large because I can make my transverse dipole smaller and smaller, and then this ratio becomes larger and larger. And it turns out, yes, there is no limit to the apparent shift of the position of the emitter. It gets, if I make this ratio larger and larger, so more elliptical in this direction, and at the same time, this is important, I reduce the numerical aperture of my observation optics, then I can get larger shifts, significantly larger than lambda over 2 pi. So we did this experiment with a nanoplasmonic emitter. It's just a gold nanoparticle with a diameter of 100 nanometers. So in order to place the gold nanoparticle in front of our imaging system with a numerical aperture of about 0.3, we use, again, sub-wavelength diameter optical fiber, but here we just use it as a mechanical support, if you wish. Now, however, if you have this fiber near the emitter, then it will still scatter and reflect and diffract light, so the effects that we are after would not be easily detected. So what we would like is actually to have this emitter more or less suspended in free space without any dielectric around it. Of course, this is not easily possible, so what we did instead is to, once the emitter was placed in front of our camera, we placed just 2 half-ball lenses in front of and behind this emitter, and then we filled the gap between the two with an index matching fluid, such that we end up with a solid immersion lens, a 4 pi solid immersion lens. The emitter is in the center so that the light that it emits hits the surface of this lens at a right angle, thereby effectively increasing the numerical aperture, of course, of our imaging optics from 0.3 to 0.4. Okay? And now we want to see the apparent position of this emitter by fitting the centroid of the point spread function. So what we do is we illuminate this emitter with light. In this case, it's 685 nanometers wavelength. And for technical reasons, it's not exactly at a right angle. It deviates from the right angle with respect to the optical axis by 7 degrees. And we put a half wave plate and a quarter wave plate such that we can now illuminate it with sigma plus or sigma minus polarized light. And as a reference measurement to know where the particle really is, we send light from the side, which is linearly polarized. So this is our reference measurement. So now observing the position of the particle as a function of polarization, we start by first measuring the point spread function in the linear case, and so this is experimental data, okay? So, and what you see is that we get a nice, actually, you can very well fit it with the Gaussian point spread function, and what I indicate here with this dashed circle is the 1 over E intensity of this Gaussian, of this spherical or cylindrically symmetric Gaussian function that we fit to the point spread function in order to determine the position of the emitter, and then the emitter in this measurement is on the optical axis. Okay, so this is our definition of it's on the optical axis. And now we illuminate the emitter with light that comes from a direction orthogonal to the screen and which is circularly polarized and turns counterclockwise. So this corresponds to this ellipticity ratio being -1, okay? And then indeed we see, and you even see it with your eye, if you look at the point spread function here, that actually it's shifted with respect to its initial position, and if you fit it, then you see that it is shifted by about 80 nanometers, okay? And if you now change the sense of rotation of the field from counterclockwise to clockwise, you see that it's shifted in the opposite direction again by about 70 nanometers here, okay? And if you now make the light elliptical, then for an ellipticity ratio or the two axes here being about a factor of 2 different, you see the shift is double the shift for circularly polarized light. And if we now change the sense of rotation of the elliptically polarized light, it shifts twice as high upwards. So if we now plot the fitted shifts here as a function of this ellipticity, then we see that they indeed lie nicely. So this is the apparent displacement of the emitter as a function of dipole polarization ratio, and we see that for this experiment where we had a numerical aperture of 0.4, we have a nice more or less linear shift of the apparent position of the emitter as a function of the ellipticity of the light. And we did many more measurements for this experiment, and then you see that indeed at least from minus circular to plus circular, it's really well fitted by this very simple expression which is linear in the ellipticity ratio. For larger ellipticities it starts to deviate because the numerical aperture is finite here. But you can do a full theory of propagating the waves through the optical system, and then you see that you can indeed also understand these effects of leveling off of the shift. And we also did to show that the shift within this range here is independent of the numerical aperture. We did the same experiment with a numerical aperture of 0.6, and you again see that the shift is nicely linear and described by this very simple expression here. And I would like to stress that here the overall displacement from one extreme to the other is 470 nanometers. Okay, this is 4 times the particle diameter. Okay, so this was purely classical optics, but of course it would be nice to now also demonstrate this effect in the most fundamental setting, which is a single atom emitting single photons, and then seeing what Darwin described as being a photon being born 10 to the minus 5 centimeters away from the atom. Okay, and for this, in the group of Rainer Blatt, we used a single barium ion in a linear Powell trap here. And we have an imaging lens near the trap with a numerical aperture of, again, 0.4. And we have some more elements here, which we didn't have in the other experiments. And this is necessary because it turns out to be pretty hard to convince a barium ion to emit circularly polarized photons permanently, because the level scheme of a barium ion, or the strong transition that we drive, corresponds to a J equals 1/2 to 1/2 transition. So while you can optically pump the atom to, say, the minus 1/2 magnetic sublevel here, when you then send sigma plus polarized light, there is a certain probability for indeed getting a sigma plus polarized photon out of the barium ion, okay? However, it can also emit a linearly polarized photon, and it can decay to another metastable level under emission of red photons. So the light here is green otherwise. And in order to get rid of these spurious photons that would spoil the effect, what we have to do is we put a polarization beam splitter here. So this polarization filter filters out this linear photons, these linear photons here, and we put a band pass filter here, which filters out these photons. So that means that per experimental cycle, we basically can convince the barium ion on average to emit about 1 photon, then it's depumped and we have to pump it back. So it's a long experiment. Per cycle you get at best a photon, okay? But still you can do the experiment for a long time, integrate, and then actually determine the shift that comes from the emission of circular polarizations on this green transition at 493 nanometers. And let me remind you that the shift that you expect then would be the shift between the two circular polarizations would be lambda over pi, so plus lambda over 2 pi and minus lambda over 2 pi. So it should be 157 nanometers. And so here we then did just the same thing as for the gold nanoparticle. We recorded the point spread function or in the two situations. And here you don't see it by your eye because the pixels are relatively large. However, take my word for it that using these techniques of centroid fitting, when integrating for long enough and having a stable setup, which is challenging, you can determine the position of the ion to better than 10 nanometers here. And then it turns out that the apparent shift of the two positions of the ion is 158 nanometers, which nicely corresponds to the expected value, okay? And I would also like to stress here that this is actually 1,000 times the diameter of a barium ion, okay? So it is indeed justified to say that here we are seeing a single atom where it is not. And I mean, this means, for example, that if you now had, say, an electron gun and you wanted to shoot the ion and you were vising optically, okay, then you would have to do the same as somebody who is fishing with a bow, okay? So you would actually have to aim low in order to hit the actual fish or the actual ion, because the apparent ion is shifted in position. However, for the case of the bowfisher here, there is actually a dielectric medium, and so it's in a sense not surprising that there are those shifts. But the effect that I was describing happens because of the coupling of the ion to a free space mode, which is perfectly symmetric and defined by a cylindrical lens. So in summary, I showed you that the chiral coupling of the spin and the angular momentum of a single dipolar emitter leads to systematic errors in the position determination when using the centroid fitting technique, which are on the wavelength scale, and we demonstrated this shift by measuring the actual and apparent position of a single atom. And we also did the same with a gold nanoparticle, where we could then also explore the case of elliptically polarized emitters and showed that in this case the shift even becomes larger and that the shift is largely independent of the numerical aperture and of defocusing. So where can all this lead to? First of all, it's obvious in a sense that these findings may affect super resolution microscopy. At least when you do super resolution microscopy, it's good to be aware of this effect, because you have to make sure, if you want to reach the state-of-the-art resolutions, which go down to a nanometer and even below nowadays, okay, that your emitter does not emit any degree of ellipticity. For determining the position to a nanometer, you actually have to have ellipticity, or the wrong component of the dipole, being like 30 dB below the component that you are usually considering. And that is maybe challenging in certain settings. The shift may also be useful if you want to now locally probe the polarization of a light field and or the polarizability of the atoms. And finally, I would like to stress that the effect that I showed here is not limited to optics. It actually occurs for any kind of wave that carries transverse orbital angular momentum. Okay, so that means that it may, for example, affect the localization of remote objects which you image with scanning imaging radar or sonar. And it would, for example, also alter the apparent position of astronomical objects like binary stars or black hole mergers that you detect through gravitational waves, where now you have optical and gravitational wave signals, and you can nowadays correlate them. And if you had a fine enough resolution, you should see the gravitational waves coming from another position than the initial, than the eventual optical or gamma flash. So with this, I thank you for your attention.
Very good. Time for questions or comments? Yes.
I've got a question. So if you apply the same thing to plasmons, for example, like with what you have started, so you get rotating dipole and then you got this rotating plasmon. So will be the effect of the shifting the same, or because now it's surface wave and decays like less fast, so will be the shift the same or different?
So if your plasmon wave carries an angular momentum in the plane. So I mean, so plasmon, I guess we're now considering a two-dimensional phenomenon and try to find the position of the source of a like emitter of plasmon waves in a 2D setting. And if your plasmon wave now carries orbital angular momentum with respect to the direction normal to your film, to your metal interface, then if that orbital angular momentum is 1 h bar per photon, you would see a shift of this plasmon source by lambda over 2 pi. If you, however, have a larger, because in principle this wave could now carry larger orbital angular momenta, say 2 times h bar per photon, then you would see a shift which is twice as large. Okay, and for example, when you look at whispering gallery modes, where you have like 180 angular momentum, and you look at them, it's quite exciting because you see the light. If this is my, say, microsphere resonator, and you have light spinning around like this, you see the light coming from here. So the light is born like 10 microns away from the resonator, because the angular momentum the transverse angular momentum is large. So it depends on the magnitude of this angular momentum, and if it, in our case, it was 1 h bar because it comes from spin momentum coupling, and the photon carries 1 h bar of spin momentum, so it can only convert to 1 h bar of orbital angular momentum. But if you have any other wave which can carry larger angular momenta, the shift will become larger.
Yes, please.
I think it was beautiful and exceptionally clear. I think your talk, if I may, is a wonderful opportunity to clarify some discussions yesterday about chirality, and you beautifully defined the difference. On one side, chirality or circular dichroism is an effect where you get a rotation of polarization. This is biisotropy with imaginary coupling terms. And what you have here, what you define here in condensed matter physics, is where you have opposite-handedness on the two sides of the axis of propagation. But related to the discussion we had yesterday, I want to emphasize that the second thing is totally reciprocal in principle, because half of the wave going to the right sees one-handedness, and the other one sees the other-handedness. So the only way you can break time reversal symmetry and get non-reciprocity, as you perfectly know, is to put a ferrite, for instance, and bias it with an external field so that you can break time reversal symmetry only on one side. So thank you very much for the opportunity. So chirality is reciprocal, but it is different propagation in different directions in the sense that you said it. So I think this is able to clarify.
I absolutely agree with everything you say. Maybe I can add that this spin momentum locking of light, and maybe because it gets clumsy when you say it, but if you wanted to be perfectly precise, what I would have to say is not the spin flips sign, but the local spin, electric spin density. It's a local effect, and this is what you say. The local spin density points in one direction above the waveguide and in the other below the waveguide, and if I average over the transverse dimension, there is zero spin, of course. And if I now want to take advantage of the spin momentum locking, I have to put a local probe, because that sees the flipping. And then I would just like to add that, yes, if you now put a ferrite where there's a magnetic field, this is what breaks time reversal symmetry, it's the magnetic field. However, in our experiments, we had a magnetic field-free non-reciprocity by spin polarizing the atoms. It turns out that a spin polarized atom, even in the absence of an internal magnetic field of the atom, it doesn't have to do with the magnetic moment of the atom, actually reacts differently to one and the other circular polarization because of Clebsch-Gordon coefficients. So the spin of the atom also transforms like a magnetic field. It has the same time reversal symmetry properties. So in order to reach non-reciprocity, the canonical things are B field, or time modulation or nonlinearity, but I think we should add spin because it transforms like a B field.
First of all, thanks for a fantastic talk. This is the very best I've probably heard in the last 15 years. Honestly. Congratulations. But, and I have a question. Can you discuss some of the implications from palm microscopy in particular?
Yeah.
Where you look at the points where if I have a set of centers which luminesce, some have different polarization. It could happen in certain tissues. I'm going to distort quite significantly the image. You have presented the opportunities, but I see also something that is detrimental, right? So can you elaborate on it?
So we elaborated on it for the last 10 months with the Nature referees, who were biologists and said, I don't give a shit, my dye is linearly polarized. And it rotates in space and averages. And we never wanted to get into that discussion because I just want this to be understood as a beautiful physical effect. But indeed, there are implications also in the setting of randomly rotating, linearly polarized dye. Okay. First of all, the fact that linear dipole emitter rotates does not mean that the emitted light is unpolarized, because when you drive the emitter with linear polarization, for example, then of course it will scatter more light when it is aligned with this driving polarization and no light when it is orthogonal to it. So that means that for that simple example, you see that there's a residual, there can be a residual polarization of the light emitted by a randomly rotating emitter. And if you now accept our claim that the statement that a dye is a linearly polarized emitter, and it turns out that when you go through the literature, it's almost religious, the belief in that, this is of course not correct to the precision that you would need to exclude the wrong polarization component. If I take polycyclic dye, okay, which looks like a small piece of rectangular piece of graphene, then of course there is a dipole also in the orthogonal direction. I have the largest dipole like this. This dipole has a different resonance frequency, and thus it will have other different amplitude when I drive the dipole. But if I now drive such a molecule with linearly polarized light which is tilted, then the fact that I'm detuned from one of the two components makes a phase shift which exactly produces elliptical polarization. Okay? And I would also like to stress that here we don't need circular polarization, because what we saw is that the worst that can happen is to have small elliptical polarization, but with a large major axis pointing towards you. So I don't say that everything that has been done in ultra-resolution microscopy is wrong, don't get me wrong. Most situations will not suffer from this. But for example, if you freeze a dye in a cryostat in order to label a protein and then claim sub-angstrom precision for the determination of the position of the different dyes on my protein, I would think that you get into trouble, because your solid matrix will distort your dye and will make anisotropic complex valued polarizability that creates spurious ellipticity in the emission of light. That is what I think, and I would like to do the experiment. Exactly.
Like a lot of cancerous tissues, they are birefringent.
Exactly.
That's going to be a mess. You're going to have a lot of mistakes.
Absolutely. So once you have a birefringent medium, then your linear dye, even if you believe that it's linearly polarized, will emit something that is no longer linearly polarized.
Thank you very much.
Thank you for your clear presentation. And my question is, if the object is moving, and what's the phenomenon appears, and can we consider modified by Doppler effect, modify the frequency? That's okay?
So I find this a very interesting question, because sometimes when I present this, then one comment that comes up, and I don't yet know, and that is the same thing I will say to you, how to respond, is that some people would say that there is a kind of Doppler effect because the wave somehow moves somewhat towards the emitter above and somewhat less towards towards the camera or the observer, and somewhat not. I'm not sure. So I mean, I think that a transverse motion of the emitter will not perturb the effect, and whether the effect in itself can be understood as some kind of Doppler shift in the transverse direction of the wave that comes towards you, I have not yet found a good explanation.
If you take the proper component of the motion, you know, like the Doppler effect in all 3 dimensions of space, you should still have a Doppler effect, even though the motion is perpendicular.
Sure. No, I agree, and I mean, in the end, the effect that you see comes from a finite numerical aperture, and then when I start moving the emitter, I do get Doppler effects on one side and the other side of my microscope objective. It's just that, like, we have not analyzed that, like, quantitatively to explain the effect in other ways. So the most simplest explanation is due to the phase front or the interference, and this explains it quantitatively.
Yes, Martin.
Okay, so what happens if you focus circular polarized light? Because then you have also longitudinal spin component. So how does the bookkeeping work?
When I focus circularly polarized light, which, I mean, this is focusing circularly polarized light, but I guess you mean with a spin that points towards the observer,
yeah.
okay?
So how do you keep track between the longitudinal and transverse spin components?
Yeah, so actually when you look at the spin momentum coupling of a circularly polarized wave, then due to spin momentum coupling, you still get longitudinal components. These give rise to transverse spin components, but in addition you have the longitudinal spin component, and now I need my 2 hands. So if then this is the optical axis, before the plane of polarization of my circular polarization, if I take linear polarization, is like that, and I have pure transverse spin. If I now have in addition the longitudinal spin, what happens is that in the paraxial case, then the plane of polarization is just facing you like that. And then with spin momentum coupling above the beam axis, it gets tilted like this. So the polarization ellipse turns like this. And below, it turns the other way around. So then you understand that the whole thing is indeed now azimuthally symmetric, what you expect from a circularly polarized emitter, because the plane of polarization looks like that, and then it looks like when you turn it around, it changes sign. Okay, so this is how the whole thing distorts the focusing of a circularly polarized emitter.
I have one question. I wanted to ask, can you comment on the intensity changes as the ellipticity changes and you scan off axis? I guess these plots you were showing were all normalized to the peak in your CCD.
Okay, so what happens when you, now we talk about a free space situation and you take a focused Gaussian beam. Then the transverse spin component is proportional to the field derivative of my Gaussian mode. That means that it vanishes on the beam axis and it becomes largest when I'm about halfway down the Gaussian where the slope is steepest. So that means that when I plot the ellipticity as a function of position, then it looks like, for also what I showed here, I have to now go to presentation mode. So it looks like that. So you have a largest longitudinal field component here, which interferes and gives me also about there the largest ellipticity. But when I then go into the wings of my Gaussian mode, then it looks more and more like a plane wave, and it gets linearly polarized again. Okay, so there is like maximum ellipticity that occurs, and that depends on the waist. So it's larger when the waist of the Gaussian mode is smaller, and it occurs away from the beam axis. And the effect we see, the shift of the apparent shift, comes from a competition of the E squared, just modulus E squared going down like a Gaussian, and the ellipticity going up linearly when you go away from the optical axis initially. And then it's obvious, since the Gaussian only goes down quadratically and the ellipticity goes up linearly, that I get an optimum of coupling, which is shifted away from the axis. And that occurs independently of the waist, interestingly in that case, independently of the waist at lambda over 2 pi away from the optical axis. So that is what is independent of the focusing. So whether I have this waist or a micron waist, I will always have the largest coupling to that mode lambda over 2 pi away from the axis.
Thank you. Any more questions? If not, let's thank Arno again for the great talk.
Thank you.